So now that we have discussed the power rule for derivatives, we can actually apply it in specific scenarios. So we have this example here where it gives us a function and it asks us to find the equation of tangent line at x equals -12. So if we're writing the equation of a line, we are going to need to use point slope form. It's always the easiest way of approaching this question. So x1 and y1 represent the coordinates, and then the m represents the slope. So the coordinates, well, we know that x is equal to -12. So I already know in the parentheses I'm going to have x plus 12. The y value is found, the y1 is found by figuring out f of -12. So if we plug in -12 into the function, we get -5 times -12 squared plus 11 times -12 plus 8. All right, so this is -5 times 144. And again, all this can be done with a calculator. 11 times -12 is going to be -132 plus 8. And -5 times 144 is -720 minus 132 plus 8. Right? And so if we add all that together, we get 844. -844. So we're going to have y plus 844. So then we still need to find the slope. So to find the slope, now that we know the power rule for the derivative, we can find the slope by using f prime. So f prime, so first we have to figure out what f prime of x is. We can't plug in -12 yet, right? So the power rule only works with x's or variables. So power rule says if I take the exponent and multiply it with the coefficient in front, we get -10x, drop the exponent by 1 to the first, plus 11 times the exponent of 1 is still 11. And then x to the 0, so I don't have to write anything there. And then the constant just goes away. So there's f prime of x. And so then if we do f prime of -12, I can plug in -12 into this. So -10 times -12 plus 11 is 120 plus 11. So 131. And so that's our slope. Okay, so that is our equation for the tangent line. So again, the steps were to use the original function to find the x and y coordinates, and then to find the derivative using the power rule, and to plug that in to find the slope. Okay, so the next example here is an example where we have to make a piecewise function differentiable by finding out the specific values for a and b. So if we first, continuity needs to occur. So we need the limit of f of x from the left and right. The possible discontinuity, possible non-differentiability is going to occur at -2. So we need to figure out the limit as it goes to -2 from the left and make it so that the limit as it goes to -2 from the right is the same. And I guess while we're at it, f of -2 also needs to be there. And that's actually given by the fact that the inequality here, so really these two things are the same. Okay, so let's do the continuity aspect of it first. So we have the limit from the left is going to be 2a times x. Well, x is going to be -2 plus 8. And the limit from the right is going to be the bottom piece of the function here. So b times 2 squared minus 3 times, sorry, -2. -2 plus 6. So we get, when we simplify this, we get -4a plus 8 equals 4b. And then this becomes plus 6 plus 6, so plus 12. So we have an equation that has two variables in it. So now the differentiability piece comes into play where we have to get the derivatives of the left and the right to be the same. So we need the limit, maybe I'll change colors up here. We need the limit of f prime of x to equal the limit of f prime of x. And again, we're doing this from -2 from the left and -2 from the right. And so if I do the derivative here, so f prime, I use the power rule, right? The exponent's of 1 here. So if I take that coefficient, or that exponent and multiply it with the coefficient, we get the top piece has a derivative of just 2a plus 0. The bottom piece, when I apply the power rule here, has a derivative of 2bx minus 3. And again, this is still for the same inequality. So as x is less than -2 for this one, and x is greater than or equal to -2 for this one. So when I do the limit as x goes to -2 from the left, we get 2a. If we do the limit of f prime as it goes to -2 from the right, we get 2b times -2 minus 3. So we have 2a equals -4b minus 3. So now you can see we have a system of equations. We have two equations, and we can line them up and solve it. So if I write it as -4a plus, I guess while I'm at it, maybe I'll move this over to this side by subtracting the 8. Right, so it's really -4a equals 4b plus 4. And then the second equation is this guy over here. We get 2a equals -4b minus 3. And that works out really nicely because if I add these two equations together, the b's cancel. And so we get -2a equals 1 and a equals -half. Now I can substitute back in to find out what b is. So we have, I could pick either of the two equations. Maybe I'll just go with the one that's 2a. So we have 2a, let me change colors up again. 2a equals -4b minus 3. So we have, if I plug in -1/2 there, we have 2 times -1/2 equals -4b minus 3. So we have -1 equals -4b minus 3. And if we add the 3 over, we get 2 equals -4b. And coincidentally, not always going to happen this way, but coincidentally, b is also -1/2. And so there you have it. You have a function, a piecewise function that should be continuous and look like a smooth curve. So you can see here, I've actually graphed the function with sliders, right? And so right now A is 0.9 and B is 0.6. So you can see that as I change A, right, we needed A to be -0.5. There's that. And if I have B as also -0.5, we will get an equivalent answer, or we'll get a function that's continuous. So if I change this to -0.5, you can see right there, it appears to be continuous and differentiable. And so there it is satisfied. Okay.